Welcome, dear audience. This is a great pleasure to be here for me. Please let me start with a question. Have you ever been in a situation where you were struggling with testing, where you had to refactor a whole class just because of testing? Or perhaps, have you ever been in a situation where you had to refactor a significant part of your application because you wanted to add a few new tests? So this presentation is about to ease the burden in certain cases when you have some struggling with tests. My name is Gábor Márton. I'm a PhD student at Budapest, Hungary. And I'm going to talk a little bit about the problem I'd like to solve here, and a few words about the existing solutions to the same problem. Then I will present our solution and our approach. Also, I will have a few words and a few slides at the future of this research. So imagine that you have a simple server class so this class really handles requests in multiple threads. And for some reason, we have a mutex to synchronize between these threads. And if we can acquire a lock on a mutex, then we will do something. Otherwise, we will do something else. And this behavior might be really important for some reason. So we want to write tests for this behavior. How could we achieve that? So one approach would be to just simply create a runtime interface which hides the abstraction, and we would have two implementations, one for the production code and the other one for the test code. So in details, actually we would use the different implementations in this way. I'd like to draw your attention that the ownership of the mutex in the original faux server class has changed. So the original server class is no longer the owner. Because of the interface, actually we receive a reference or a pointer to that interface. We have to somehow inject a dependency from outside. And for that injection, actually, we may call it as a dependency injection. But for that injection, we added a new public constructor, or that could have been even a sector. But the point is that we had widened the public interface just because of testing. Another approach would be to do something similar, but with compile time polymorphism instead of runtime polymorphism. So the idea is the same as previously, but this time we have to make the whole class to be a template class, right? And this might be a burden. Just think about the original structure, and the original class might have been scattered around in several translation units, and this time we made it a template. It has to be in a header file. So both this approach and the previous approach has some serious disadvantages and some serious effects on the original structure we had. This is what I call struggling with tests. On the other hand, there are certain tests or certain way of testing where we don't have to change the structure. We don't have to change the original structure. This testing is called non-intrusive testing. And this can be really useful also in case of legacy code bases. Let's say we have a big legacy system without any unit tests. We would like to do some further development on that system. So actually we should have some tests in order to verify that we don't wreak havoc the existing behavior. So non-intrusive testing is not a new thing. There are tools for non-intrusive testing. For example, LD preload, the environment variable, can be used to to change a shared library for the purpose of testing. However, setting up a text executable to be loaded with a different shared library can be cumbersome. We have to use somehow the build system. So it is not trivial what's happening. It cannot be seen in the test code, in the source test code right now, how we set up the test itself. Also, another tool is the so-called instrument functions compiler instrumentation. This can be found in GCC and in Clang as well. It emits hooks at the beginning and the end of a function. So this way we may alter a dependent function's behavior. So once again, what we want to achieve here is to be able to write tests without changing the original structure and keep the test setup as simple as possible and as visible as possible. In this example, we say that, okay, please replace the trilog member function with a test double. And with the help of the test double, we can actually exercise the units under test. That's how simple the motivation is. So our solution is actually a compile time instrumentation. We instrument every call expression. And this has an advantage in case of shared libraries, for example, because we don't have to recompile the shared libraries. We just have to recompile that part of the code where the call expression itself is. So we can easily replace system functions and other third-party functions in our system. The architecture of this research, this prototype, consists of three main parts. There's a backend where we modify the LLVM IR. That's where we emit a new hook. And there's a runtime library where we have to implement the mapping of the original and the substitute functions. Also, there's a language-specific front-end which handles some C++ specific difficulties. I will just have a few more words about that soon. So here's what's happening in the LLVM IR. We take the original call expression and compile time we emit a hook function, and based on the result of that hook function, we decide whether we have to call the original function or the substitute function. It's so simple. Actually, currently, the prototype we have is implemented in a way that we modify the code generation part in Clang. However, this would be better to implement this as an LLVM pass, because that way it would be independent from Clang and from the language front ends. So the runtime library is actually nothing more than a lookup and a hash map. So if we have an entry in a hash map, that means we have to replace a function to a substitute function. Actually, we use a technique which may seem familiar to you, the shadow memory technique. This has been used in address sanitizer, thread sanitizer. So instead of using difficult hashing, we just simply map the virtual memory and we offset directly into the shadow memory. This can make the hashing, the hash map itself a little bit more efficient. Also, this runtime library has the task to provide the C and C++ API. In both cases, we may call the substitute macro with all capital letters. So we just simply say which function to replace with which counterpart function. This thing itself can be really difficult in case of virtual functions, because as you may know, that we cannot just get the address of a virtual function. So that's the exact reason why we created a C++ specific frontend, where actually we created a new unary expression, which is really similar to the existing address of unary expression. But the type of this expression is different in case of virtual functions. So it is something like we can get the concrete address of that function as it is in the text segment. Anyway, this feature is already implemented in GCC. However, it is not in Clang. Also, there are very good reasons why this was never implemented. So this feature is only available when the testing-specific instrumentation is turned on, and this is hidden away from the users. So this is only for being able to get a unique identifier for a virtual function, so we can replace that with any other functions. A few words about the future. Well, since nowadays we instrument all call expressions, this can be really slow. So it's like, it has the performance similar to the F instrument functions instrumentation. Or this is a little bit faster because of the shadow memory. So one idea would be to just instrument only those call expressions which are really needed to be replaced. We might be able to use attributes on function declarations, but this can be really hard, and it's not an easy solution. Also, some idea would be to do similar instrumentation what's being done in the X-ray system. So they actually emit no operations, which can be executed really fast by the CPU. And the idea here would be that, okay, replace the no operations only when we do really want to do this substitution. Again, some alternative approach would be to do the whole thing on the AST level. So some of you may have known that there's a nice little part of Clang, the AST importer, which are used only in LLDB and in cross-translation unit static analysis. This might be reused in a way to do transformations on the abstract syntax tree level. So we could do the whole thing instead of instrumentation at the level of the AST. Thank you very much. Please shoot me with your questions.
Okay, so we have plenty of time for questions. Does anyone have any questions?
Did you make any attempts to test this thing for correctness? I mean, like substituting for itself and then running some tests?
So, correctness. Actually, yeah, we should have some sort of checking whether the substitute function and the original function has at least the same prototype or the same type. Yeah, that's right. That is still a missing feature in the prototype, that we do not do any kind of checking, but this could be easily implemented with some sort of template programming or C++ metaprogramming. Again, I don't know, is that an answer to your question? Okay.
I would have another question. I'm not sure if it was on your slide, But how do you handle the this pointer? So you replace this with mutex, but as far as I saw, you didn't pass in the pointer for that mutex instance.
Yeah. So the first parameter of the substitute function will be a pointer, which actually has the type of a pointer to the mutex type. So it's like passing the this pointer as the first parameter.
Okay, thanks.
Okay.
Is there any other questions? Someone trying to maximize the amount of exercise I get.
So I might misunderstand something here, but like, do you have a concern that using this technique too much ties the testing code to the code you are testing? Like, if you have an ability to change arbitrary functions inside the code you are testing, then suddenly the test starts to rely on all the private implementation details it ideally should not care about, whereas in dependency injection sort of has to explicitly specify those.
Okay. If I understand your question correctly, then could you please rephrase your question?
So I think the question is about the tight coupling between the tests and the implementation details rather than the expected behavior of the things they're testing.
Right.
Is that?
So, yes, this could create tight coupling with the test. That's right. However, this tool can be a nice complement in certain cases. It's not a new theorem, I would say. It is not a word-saving tool, but it can be a tool when you have certain cases where, for example, you have a legacy system and you don't want to change the legacy code because you don't have any tests at the moment. Or it can be also a tool in this, for example, as you've seen in this running example, if you don't want any structural changes, but it has a price, as you've seen. It has a price, it can introduce new dependencies. But as engineers, we have to negotiate between bad and good or more bad things.
Okay, I think we have time for one more question. Oh. You were a fraction slower, but you're much closer, so you win.
So let's see. Have you thought about chaining instead of replacement?
Chaining.
So to be able to have a pre-step and then call the actual function in a post-step.
No, I didn't think about that.
So
it's a good idea.
Okay.
Okay, so thank you very much.